Okay, what if, I do apologize jumping around, okay? What if now the point, okay, the point that we want to find, now let's say Vy is starting from the top, right? The point that we want to find is down here, and it's our point beta. Okay, beta is the point that we want to find. So how do you take your first moment of area? Anyone? Is it going to look like a T or is it going to look like a square? Anyone, please. Where is the area that you're going to take? By looking at all the 5 rules. Anyone? It's going to be where? This is the
Would it be like starting from the bottom? Yeah.
Yeah. It's going to be a square. Yes or no? Right? And then I have a next question for you now. I have the next question for you now. What if now, okay, what if, same thing, everything the same. What if now we want to find the stresses at point, okay, we want to find the stresses at my blue dot count here. I call it my point C. Okay. Which area do you take? Anyone?
Would either one be okay? Because neither
Again?
would it not matter, because like neither place where we take Q would like cross the centroid.
Yeah, does not matter, because you can take it from the top. You're absolutely right. Okay. Now, Jihad, why do you make that statement? You are absolutely right, but why?
Oh, because like the point C is like directly on the centroid, so therefore like whether we take it from the top or the bottom, it's not going to cross over.
Yeah, the area. Okay, if it's centroid means what? The area at the cross-sectional area at the top and the cross-sectional area at the bottom is going to be exactly the what? The same. Yes or no? Sorry, the first moment of area at the top, not the cross-sectional. The first moment of area at the top and the first moment of area at the bottom. Okay, so if I call this top and I call this bottom, right? So the first moment of area Q top is equal to the first moment of area of the Q bottom. It's exactly the same. Okay, it's exactly the same. So for this case, does not matter whether you take from the top or you take from the what? Bottom. Very interesting, right? This is only possible, right? If and only if we obey the 5 rules. If you don't obey the 5 rules, oh man, okay, when I started teaching this topic in what, 2016, when I did not write all these rules, every student get really, really confused. Even I get confused. Okay, obey these 5 rules, okay, then that's where things will be fine. Okay, that's why I say this topic is like what? It's like electrical engineering. You have to know when to apply constant voltage and when to apply constant current. You cannot see the voltage, you cannot see the current, but you have to apply the rules. Exactly the same. Okay. Exactly, sorry, my mic just dropped off. I got too excited. Okay, exactly the same as doing electrical engineering. Okay, now let's quickly go into an example. Okay, let's quickly go into an example where we can plug numbers. Now I know if you cannot plug numbers, you get frustrated. I also get frustrated if I cannot plug in numbers. Okay. So I'm still going to copy the I go, hold on, undo. Sorry, I get really wind up when that happened. My bad. See whether does it still happen. Okay, I'm not going to fight over it. Okay, so I'm going to do an example. Okay, so you can find this example on last week's notes. Okay, last week's example. Right. So this is our example number 1. Okay. So for the beam show, determine the shearing stress at point A and at point B. Okay. So I'm going to write out some information that I already calculate that you also know how to get very quickly. It's getting the centroid and the first moment of area, which I will not do over here. Okay. So the centroid, okay, capital Y bar is equal to 35 millimeters from the top. And then the IZZ, the second moment of area, right? The IZZ will be equal to 5.8133. That's 10 to the power minus 6 meter 4. Okay. So we are going to find the maximum or the shear stresses at point A and at point B. Okay. So we are going to draw transformation. First of all, so this is our X. This is our Y. And this is our rotation about Z. And that is the cross-sectional view. Okay, the cross-sectional view will look like this. That this is a transformation. Okay. So the cross-sectional view. This is Y. This is Z. This is rotation about X. Okay, so I put down here cross-sectional view. Okay, so first thing, how to solve this, I'm going to write down the procedure. First, we have to draw a free body diagram first, and then we have to calculate the reaction at point A and point B. Okay, then we have to construct the shear force diagram. Then after that, then we can determine the shearing stress. At point A and point B, and to determine the shearing stress, we have to calculate determine the first moment of area for point A and for point B. And then I'm going to do an extra thing, so probably we will finish this example on Wednesday, is the shear stress distribution equation. This is not in the question, but I want to show it to you. Okay, shear stress distribution equation. Okay, so by looking at the problem again, I'm going to copy the problem. We are going to draw. Sorry, I should not move my page so much. We're going to draw the. We're going to calculate our reaction at point A and reaction at point B. Okay, so we're going to draw a free body diagram first. Okay, so we know that we have a beam simply supported, and we know that we have a AY, we're aware that we have a BY, and then we have a load exactly applied on the center, and the load is coming at 100 and I think it's 180. It's so small that I cannot see. Yep, 180. Okay. So from here, we are going to perform static analysis. Okay, so I'm going to do summation about forces or moment about the z-axis at point A. The whole thing will be equal to 0. So you'll be 180 minus 180 times 10 to the power 3 multiplied by a distance of 0.5, okay, plus by 1 by. The whole thing will be equal to 0. So by is equal to 90 times 10 to the power 3 Newton. And then the next thing you do is you can take summation of forces in the y direction, right? So ay minus by 180 times 10 to the power 3 plus by 90 times 10 to the power 3, which is your by, and you will realize that ay is equal to 90 times 10 to the power 3. Okay, so from here you can immediately construct your shear force diagram. So on our shear force diagram, we can call this x. And then your vertical, this is your v, which is times 10 to the power 3 Newton. And we know that we are at 90. And then I'm going to go for minus 90. 0. This is 0.5. And this is 1. Okay, so we're going to construct our shear force diagram now. So realize our shear force diagram will go from 90, come to the horizontal. Okay. And then it will drop by 180. Okay. Then you go horizontal. So from here, we realize that V max or Vy max is equal to 90 times 10 to the power 3 Newton. Okay. Now, why I want to show this step is this for this reason. A lot of times, okay, a lot of times students are, or even some engineers, gadget engineers, okay, they will use the 180 as the V max, which is wrong. Okay, we realize that by constructing your shear force diagram, the maximum V max will be 90. Okay, and some of you might say, Eugene, what if I take the your maximum negative like minus 90? Your answer will still be the same. I show you already, right? I show you before whether you take positive 90. Positive 90 means it's coming from the top, right? Or negative 90 if it's coming from the bottom, right? This is coming from the bottom. Your alpha is still the same. Yes or no? Right? The alpha is still the same because the area of consideration is still what? It's still the same whether the shear force is coming from the top or the shear force is coming from the bottom. I.e., it does not depend on where the shear force starts from to get your first moment of area. You have to get this concept really, really correct. Okay, because mechanical engineer, we see to what? To believe. I'm like that. I'm the doubting Thomas, the biggest one. Okay, this is where we have to apply the rules. Okay, right. So from here, we found that our Vmax is equivalent. So now we are going to find. Okay, we are going to find our our first moment, our shearing stress at point A. Okay, we're going to find our shearing stress at point A. So what I'm going to do is I have another diagram that I would like to use. Okay. Ay. Okay, we are going to find the shearing stress at point A. Okay, So we're going to find. So if I were to draw our forces, so we know that this is our Vy, right? That is our Vy, and this is our transformation. Y, Z, rotation about Z, about X. Hey. Okay. So we know that we are going to find the shear. The plate intersecting the axis is X, and it's going to be Y, and we're going to find an A. And the formula is Vy over IZZ QZ divided by T. Okay, divided by T. So what do we know? Okay, what do we know? We know that Vy is equal to 90 times 10 to the power 3 Newton. We are aware that IZZ is equal to 5.813